Hey everyone, these are notes for chapter 13.1. This is going to be a rough overview of the introduction to graph theory. If you're curious, 13.2 through 4 should be posted tomorrow, but before that we'll be going over an introduction to graph theory. First up, what's a graph? Well, the word graph means a lot of different things in math, but in graph theory it's going to be a set of vertices and a set of edges that connects them. Now that seems a little bit over the top, but don't worry. A vertex is just going to be a point, like something that we can just draw. And an edge is just going to be a line that connects the two vertices. So here's an example of a graph. Looks like this. You can see it's kind of a bunch of stuff all at the same time. I've labeled all of the vertices, or vertices. Sorry, vertice is the plural and vertex is the singular. And the edges are going to be red while the vertices are white. That's just for appearance, but as you can see that we've got an edge between like A and E and C and A and stuff like that. So when we're talking about the basic terminology, we should first start with the vertex is just identified by the letter next to it. So we might say that the top left vertex over there is an A because there's an A next to it. In this case, the graph has the names A, B, C, D, E, and F. You don't have to name them one letter. You can name them whatever you want. Maybe you can name one of them Jeffrey or something like that, but usually it's just a single letter. We refer to the edges by the two vertices in it. Technically, it implies direction. So AE means it starts at A and ends at E, and EA means it starts at E and ends at A. But since in this case the direction doesn't matter, there's nothing to indicate that it would. We just say AE usually, but that's the yellow edge. Now we can use this similar terminology to talk about what we would think of as a path, which is kind of a connecting bunch of edges together to form kind of a longer route. So something like DBAC starts at D over on the left, goes up and to the right to B, goes to A to the left, and then finally goes to C in the corner. It's not just that it's those edges in particular, it's also the root. And something like EFC is not a path because if you try to start from E to F, you'll notice that EF doesn't actually exist. There's this big gap there. I didn't put something there. There's nothing missing, or there's nothing that's supposed to be there. It's missing. And so EFC doesn't exist because EF doesn't exist. One of the ways that we can talk about graphs is by if they are connected or disconnected. And we say that a graph is connected if every vertex has a path to every other vertex. So not an edge, but a path, which is a lot looser. If this isn't true, then we just say it's disconnected. So here's a fun table. Here are two different line segments you can see, and since there's no way to get from the top one to the very bottom one, there's no path from the top one to the bottom one, we say it's disconnected. And here, this is a very connected graph in the sense that every vertex has an edge between it and all of the other vertices. Meanwhile, this graph over here, this triangle, looks like it might be connected except that there's this extra vertex just sitting by itself. And even though there's no edges from it, we'd still say that this is disconnected because there's no way to get to this bottom right vertex. Meanwhile, this one, it has less edges than the top one, even though it has the same number of vertices, but it's still connected because I can get from every vertex to every other vertex. And that's basically what connected is. By the way, if two edges cross in a graph, like there's an overlap, that doesn't actually mean a vertex occurs. Sometimes this can be a little confusing, which means that it might look like certain graphs are connected, but they're not, I promise. So I'll give you an example of a slightly trickier one. So this is a disconnected graph uh, because I can't actually get from the left one to the top one. It looks like there's a root because I can kind of see this L-shaped thing, but that doesn't count because the line kind of that's a different edge. An example of a connected graph that looks very similar would be this one. Now I can get from any vertex to any other vertex. And, well, therefore it's connected. By the way, I want to point this out again. The graphs aren't identical. The one on the left has 4 vertices. The one on the right has 5. And that is kind of the big distinction here. So one of the things that we can talk about is that equivalent graphs. It'll help make the previous example kind of make a little bit more sense. And we just said that they're equivalent if they have the same number of vertices and the edges that connect those vertices are the same. That doesn't mean that the names of the vertex, each vertex is the same, and it doesn't mean that the location of the vertices are the same. So what I mean by that is we could take something like this graph from before, this time I gave it labels, and I can say, well, that's the same as this graph. And I see I've just shifted the vertical line slightly to the left, and I've given them different names. But that's okay, because the key thing is that these are fundamentally the same in that you have kind of 2 straight lines, and that's it. They're just connected. In fact, the first disconnected graph I showed is also the same as these graphs. Here's another example. So this graph, I've named it A, B, C, D, like over here. That's the same as this graph, which is A, B, C, D. Notice that this isn't an error, but the A doesn't correspond to the A. Like, in fact, the vertex A in the first part is actually vertex B in the second part. That's not an error. That's on purpose. And the idea is that that doesn't matter. These are still the same thing. And by the way, if I didn't say this earlier, edges don't have to be straight lines. There's nothing that says that they're just lines. They can be squiggly and weird and have loop-de-loops as long as people understand what they are. So that's it. Rather than just talk about the properties of the actual graph, we can talk about the properties of the individual vertices. So we can usually identify vertice properties based entirely on the edges connected to it, because that's basically all we have, just vertices and edges. So we can say that a vertex is adjacent to another vertex. Well, all that means is that there's an edge connecting them. So here is a modified version of one of the examples from before. I've added a little e here. And in this example, A is adjacent to B. So the vertex A is adjacent to the vertex B. And you can see that because they have that little curvy edge between them. But A isn't adjacent to C, D, or E. So even though this is connected, because A has a path to all of the other vertices, it's not, it doesn't mean that there's an edge between those things. And in fact, A isn't adjacent to C, D, or E. B, however, is adjacent to A, C, and D. You can see because they have those 3 things, but it's not adjacent to E. We can also describe the vertice not by the specific neighbors it has, but more just what the degree of the vertex is. And that's just the number of edges that leaves the vertex. So you can see A, C, and E, they all have degree 1 because there is one edge leaving A, there's one edge leaving C, and there's one edge leaving E. B, however, has 3 vertices. And since 1 and 3 are odd numbers, we say that they actually have odd degree. And that matters because of stuff that we're going to be dealing with in 13.2 or 3. It might also be in 13.4. But the odd or even nature of the vertex has an effect on some problems. D, by the way, has degree 2, you can see, because it has an edge that's leaving it to go to B and an edge that's leaving it to go to E. And since 2 is even, we say it has even degree. So this all seems kind of weird because they're all just dots and lines, but how do we use them? So we often try to describe real examples in a much simpler way. So we'll look at this map. This is a map of the United States. Well, it's just a map of a southeastern corner. And there's a lot of things going on in this map, but if I wanted to talk about the information on which states share a border, I can simplify this by referring to them not as states, but just as vertices. So you'll notice that I've just replaced each one of the states with just a dot, and I've given it the same label. So now you've got little Mississippi, and then Alabama, and Georgia, and South Carolina, and Florida. And now they're just dots. And we can connect them based on the states that share a border. So Florida, for example, shares a border with Alabama and Georgia Georgia shares a border with Alabama, South Carolina, and Florida. So, like, you can see that they each have kind of a different shape. And this is a pretty useful tool sometimes when we want to have this, we want to kind of just take the important, relevant information from the picture. We'll get into some more practical examples in the later sections. But for now, this is kind of a simplified map. So here's a different simplified map. This one is also kind of something you'll see on the homework. Consider this is a floor plan. You can see the empty spaces, by the way, just represent a door. And this floor plan, I've labeled all the rooms, and I've labeled the outside as H. Now, we can talk about the areas that are connected via doorway, and we can draw a basic graph for the interior rooms, like those. That's going to be A through G. And it looks like this. I've kind of shifted the points around to fit in the slide, but you can see that A through G, if you want, you can study this a little bit, but this is just, this graph represents everything except I haven't addressed the outside yet, but that's the interior. This would be the interior rooms. Now, we could add H, but H is a little weird, so that's going to be on the next slide. But for now, just think of these. But remember, H isn't the backyard, it's the outside, and that matters, and that's going to be why it's a little bit weirder. So H, since it's the outside, it should share an edge not just with B, where it seems to be like right next to it, but also with C, because you can see that right exit, and F. And F is the front room. And by the way, this is just because there's a door leading to the outside from all three of those rooms. So we can attach it to the original graph with just those three edges. It looks like this. Notice that I don't have to like loop around. I don't have to have multiple copies of H. In fact, you shouldn't have multiple copies because there's just one outside. But we can attach it, and that's what it looks like, and that's the floor plan. This could also be extended to talk about multiple floors, like you might have a second or third story, and you would want to talk about how those rooms connect in an interesting way as well. So that's worth talking about in terms of practical examples, but this is something you might see on the homework, so I figured I'd go over this problem. So that's the rest of 13.1. I know that was somewhat short. Again, I'm going to be posting the rest of the notes tomorrow. If you have questions about this or any other section, ask me via email. I'll be happy to send pictures or diagrams or just explain any of the homework problems you might be struggling with. Again, email, Canvas, or come to my office hours. That's 12 to 1. Uh, Monday, Wednesday, Friday, or by appointment, which just means you send me an email and say, hey, I can't meet during those times. Either way, that's it. Everybody have a great day.